In this module of Chapter 9, I will discuss the concept of frailty structure in populations using data on the Mediterranean fruit fly. The frailty structure that I consider here and in our Biodemography book is based on a mixture of different age cohorts in a sample that is captured in the field and subsequently monitored through death. The frailty inherent in a cohort of mixed ages is that the older individuals constitute a subgroup that is much more frail than the younger individuals. Thus, the trajectory of the survival schedules will be the outcome of subgroups at differing levels of risk. In the analysis of post-capture survival, the cohort of individuals may be heterogeneous, and this can pose unique issues for the estimation of survival. In populations of insects and other invertebrates, individuals within a captured cohort will be a single age class for species where there is synchronous emergence of adults, such as mayflies. In most other plant and animal species, a captive cohort will consist of individuals of mixed ages, and the exact composition will be unknown. Frailty, and thus the probability of death, varies with age, and thus the time trajectory of mortality for a sample of individuals captured in the wild will be determined by the age composition of the captured cohort. This age composition may change during the season or between locations. I will consider the impact of heterogeneity on survival patterns in 4 scenarios of frailty. I have 4 panels to be considered based on captive age or time since capture on the x-axis and survivorship on the y-axis. The upper left panel shows survivorship in the single age groups of young, medium, and old. The next panels consist of different mixtures of these different ages, with the upper red line depicting the survivorship of the least frail, which is to say the most robust sub-cohort, and the green line being the survivorship of the most frail, with intermediate gray lines depicting the different mixtures of each in the life table radix. Those in panel B consist of the young plus middle age cohorts. Panel C consists of the young plus old cohorts, and panel D consists of mid-age plus old cohorts. For the first case, we will consider single cohorts at different capture ages. The survival curves shown in this figure correspond to the hypothetical situation in which individuals from the wild are collected from a single wild medfly cohort immediately after emerging, that is, young only. And again at 50 days, that is middle age, and once again at 90 days, that is old age. Survival of young individuals is extremely high, that is a flat slope, through until around 50 days, at which time they begin dying off more rapidly. Note that some individuals survive beyond 125 days. For individuals collected at 50 days old, initial survival is moderate, but is substantially less than survival for young individuals during their first days post-capture. Survival then drops off rapidly, and no individuals live beyond 75 days. Survival for 90-day-old individuals is relatively short, with an extremely steep decline immediately after capture, and no individuals live beyond 30 days post-capture. In the second case, that is panel B, we will consider a cohort with a mixture of young and middle-aged subcohorts. At the time of sampling, this hypothetical population consists of a mixture of newborn, that is age 0, and 50-day-old individuals. The earliest deaths of the middle-aged subcohort drives the overall cohort survival downward immediately. The steepness of the decline depends on the relative initial number of middle-aged individuals in the cohort. As the middle-aged subcohort dies off, the higher survival of the original newborn subcohort, though now older, becomes a larger proportion of the total. As a result, the decrease in survival slows through the intermediate post-captive ages until the time when the original newborn cohort reaches more advanced ages. At this point, the steepness of the decline in survival increases dramatically. Maximum post-capture longevity is 140 days due to the presence of the newborn age class in the original cohort. In the third case, panel C, I consider a cohort with a mixture of young and old subcohorts. At the time of sampling, this hypothetical population consists of a mixture of newborn, that is age 0, and 90-day-old individuals, that is very frail. The much higher death rates of the older individuals immediately drive the overall cohort survival steeply downward. At middle captive ages, the depth and steepness of the decline will depend on the relative proportion of the older individuals in the cohort. As the older subcohort completely dies off after around 3 weeks, the overall cohort survival is determined solely by survival in the only remaining subcohort, the original newborns. This change in the composition of the cohort results in improved survival in the intermediate post-captive ages, until which time the original newborn cohort reaches the more advanced ages. Maximum post-capture longevity is 140 days due to the presence of newborn in the original cohort. In the last case, Panel D, I consider a cohort with a mixture of middle-aged and old subcohorts. At this time of sampling, this hypothetical population consists of a mixture of middle-aged, that is 50-day-old, and old-age, that is 90-day-old, subcohorts. Because the average age of the overall cohort is high, because there are no newborn individuals present, survival begins declining immediately after capture, with virtually no slowing at any time through the maximum post-capture age of 75 days. Although my specific examples in this module were based on population heterogeneity due to the differential frailty resulting from a mixture of young, middle-aged, and older individuals, the broader concept of how heterogeneity shapes mortality and in turn shapes survival is a basic concept regardless of the source of frailty. This ends Module 9.9 for this book chapter.